welcome back, and so let us continue the discussion of the turbulent flows, and we are slowly getting into the details of characterization of the turbulent flow. And first thing, we have looked at the some initial features of the turbulent flow, how they would look, and then discuss the properties of the flows. Now, where we stopped here is the situation where the system is a well closed problem or the ill closed problem, and we said a system of PDEs or closed system of PDEs for a given initial and boundary condition. If a solution exists, the solution is unique, that means the only one solution exists, and the solution is stable for small perturbation in the initial. Now, the important question which arises here, what about the Navier-Stokes equations? Are they ill posed or well posed? So, this is well posed for laminar flows. So, that is a very important point. Now, that means we mean to say this is ill posed for turbulent flows. Now, when we say it is an ill posed, that means we can say what it does not do. So, the turbulent flows do not satisfy this last condition or the third condition, that means the. So, if you say this is 1, 2, 3, so this guy do not satisfy condition 3, which is that solution is not stable for a small perturbation in the inner and boundary initial and the boundary condition. So, which means the realistic initial condition and boundary conditions always known with finite accuracy, and also the behavior is related to. So, this behavior related to non-linear term in Navier-Stokes equation, which is uj del ui by del x j. So, this is the nonlinear term, and this behavior is sort of related to this nonlinear term in the Navier-Stokes equation. So, that means which is one thing which is absolutely clear here is that for laminar flow it becomes Navier-Stokes equation becomes an well posed problem. That means it satisfied all these three conditions: solution exists, solution is unique, and solution is also stable. But for turbulent flow it does not satisfy the third condition, that is why it becomes ill posed, and the behavior is somehow related to the nonlinear term. So, that means we can conclude saying that the turbulence, which could be a deterministic chaos. So, this is what one can say about turbulent flows. Now, we will look at slightly in details. So, first thing that we will do the non-dimensionalization. So, non-dimensional form of NS equation. Okay. So, first thing that we will do, we will non-dimensionalize the system. So, for that we need some characteristics, velocity and length scales. So, we say capital U and L, and the non-dimensionalization can be done, can be achieved through this, where we can define xi bar is xi by L, T is Tu by L, Ui is Ui by capital U, and P bar is P by rho U square. So, that is what we do. Then if we write the non-dimensional Navier-Stokes, this will look like, your continuity equation will look like 0 and del Ui by momentum equation would be Uj del Ui by del Xj minus del P xi plus 1 by Re Now, here the Reynolds number Re is defined as characteristics velocity length scale by nu, which is our ratio of two forces, one is inertia divided by viscous forces. So, that is what we get. Now, we look at the scale similarity. So, already we have got the non-dimensional form. So, there are two similarity, one is the Reynolds number similarity. So, Re similarity, that is one important thing, which says that if for two flows the Reynolds number and the scaled initial or boundary conditions are the same, then the scaled velocity and pressure fields are the same as well. So, that is what you say about Reynolds number similarity. Now, at large Reynolds number, the viscous term. So, the term essentially the term with 1 by Re is negligible at large scales. So, which means there is a scale similarity which on the other hand says no dependency on RE, and other one is the holds for large scale structure of turbulence, that is the nothing but the macro structure. So, this is what from our non-dimensional Navier-Stokes equations, which is continuity, this is continuity and this is momentum, we can say there are both the scale similarity and Reynolds number similarity, and Reynolds number similarity is if for two flows the Reynolds number and the scaled initial and boundary conditions are the same, then the scaled velocity and pressure fields are the same as well. So, that talks about your RE similarity. Now, when we move to a large RE, the term which has the viscous term, that means this is the viscous term, this is our viscous term, that is what we said terms with 1 by RE is negligible at large scale, which means there is a scale similarity, that means there is no dependency on the Reynolds number, and there is this holds good for large scale structure of turbulence, that means the macro structure. So, these two things are your Reynolds number and the scale similarity. So, now that will be one more thing which to be interesting to quantify is the vorticity. So, the definition of vorticity says that if you say omega equals to del cross bar, which means the vorticity is 2 into angular velocity of a fluid parcel. So, that is small fluid volume. So, that is what we, so it is a curl of velocity vector will get you the vorticity in mathematical term, this is the mathematics. So, we can derive the conservation of vorticity. So, that how do you get that? You by taking the curl of NS equation. So, we have got this NS equation either in non-dimensional form. So, we can or in dimensional form, you take the curl of that, what we get del Wi by del T plus Uj del Wi by del Xj equals to Wj del Ui by del Xj plus nu del I by del Xj. Now, here this is our vorticity transport equation or conservation of vorticity equation, or one can say vorticity transport equation. Now, this particular term here, this term it is called the vortex stretching term. And this only present in 3D flows. Okay. Now, what it does, there is a very interesting phenomena which is associated with this particular term. So, vortex stretching mechanism causes change in vorticity of a fluid parcel by stretching and rotation of the parcel. So, this is very important concept here. The vortex stretching mechanism actually causes the change in vorticity of a fluid parcel by stretching and the rotation of the parcel. So, it stretches and also rotate the parcel. So, one can think about vorticity in global sense. This is a characteristic feature of turbulence. So, that is how we are looking at different aspect of this particular flow. We looked at this large scale similarity, Reynolds number similarity, macrostructure, microstructure. Now, we are looking at the vorticity. Not only vorticity, also the vorticity transport equation, where we have a vortex stretching term and vortex stretching mechanism. So, that is one of the characteristics feature of the turbulent flow. Now, we will go back little bit and start with some simple system like potential flow. So, which means that is zero vorticity. So, the potential flow means flows with no vorticity. So, that means there is no stretching of fluid parcel, neither the rotation of the fluid parcel. So, which means omega bar is 0. So, you can have an velocity potential and we can that one can define is del phi by del xi. Now, once you do some algebra here, so del cross u equals to del dot u minus del cross omega. So, this goes to 0 and u dot del u equals to del u dot by 2 minus u cross omega, this also goes to 0. So, these cross terms are 0 for 0 vorticity. So, for potential flow, the Navier-Stokes equation actually reduced to another famous equation called Bernoulli's equation. Which is del 2 phi by this is 0 and del phi by del t plus half minus 2 constant. So, these are the set of equation that one may have for potential flow which does not have a zero vorticity. That means the flow field assumed to be not getting stretched, neither having any rotation. Now, we will look at the equation or the governing equation with varying density. So, density is no more constant, but still we will maintain dynamic viscosity constant, and density is a function of temperature only. So, that means the density is no more constant, density is varying. So, we can have some approximate equation for conservation of mass, which will be del ui by del xi. So, this is one can note here approximate equation. When density is varying, we cannot directly write this what we have written for incompressible flow. So, this is an approximate equation. Now, the momentum conservation will have the variation of the density into the system. So, that will look like density with del ui by del t plus uj del u by del xj minus del p by del xi plus rho gi Now, we use one more equation because density is a function of temperature. So, we will use the energy equation and equation of state. So, equation of state would give me rho is a function of theta and my energy equation will get me energy equation for temperature. So, that will be in terms of del theta by del t plus uj kappa del 2 theta by del xj square. So, that is what we get. So, this is the governing equation that one can have for the varying density condition. Now, we will use one important approximation is known as Boussinesq approximation. So, we can define our reference system like this. So, this is my x. So, u will be in this direction, this is my y, v will be in this direction, this is my z. So, my w will be in this direction. So, my g will be acting on this direction. Now, first have some reference condition. So, the reference condition is 0, p naught, rho naught, theta naught. So, the equation of basic state would be 0 equals to minus del p by del z minus rho Gj. Now we want to slightly deviate from the basic state, that means small deviation from basic state. So, how do you get that? So, we will say that u naught plus u, p naught plus p, rho naught plus rho, theta naught plus theta. So, there is a small deviation from the basic state. Now, we linearize the Gaussian equation. So, the Gaussian equation that we have written here, mass, momentum, energy for temperature. So, the linearized system would look like that rho by rho naught equals to minus alpha by theta naught. So, this is my this is where alpha equals to minus theta naught by rho naught del rho by del theta at theta equals to theta naught. For ideal gas, alpha would be 1. This is my linearized equation of state. Now, my Boussinesq approximation will get me del u by del xi equals to 0, and my momentum equation becomes del ui by del t plus uj del ui by del xj, rho naught del p by del xi, theta by theta naught plus mu by rho naught. So, this is del to ui by xj square, and we get del theta by del t plus uj del theta by del xj kappa del to theta by del xj square, and this is the term what with the negative sign is the buoyancy effect. So, this is first order effect of weak temperature induced density variation. So, when the density is dependent on temperature, due to that you get to see some variation in the momentum equation. So, we will stop here and continue the discussion in the next lecture.